Good afternoon, dear students. I wholeheartedly welcome you all to the Gpat class on pharmaceutical analysis, hoping that everyone is working hard towards the success of Gpat. Owing to that, as a part of Gpat team, here myself going to interact with you all about pharmaceutical analysis subject for your better appearance in the coming exams. Hope you all will cooperate with me for training you in the better way about exams. Let's move on to general principles on spectroscopy in the today's class. What is spectroscopy? It is the study of interaction of electromagnetic radiation, that is EMR, with matter. What is matter? A matter represents an analyte, a particle, a molecule, a substance, a solute, or a sample to be analyzed. And spectroscopy is applicable to characterize a molecule. It is used for characterization of a molecule. So matter represents here analyte or a particle or a molecule or a substance or a solute or a sample to be analyzed. So to which electromagnetic radiation is passed to characterize the particular molecule. That is the main application of spectroscopy. Let's see what is an electromagnetic radiation. It is the radiation which has both electric and magnetic properties. That means it has both electric field oscillation and magnetic field oscillation when it is propagated in a vacuum. Electromagnetic radiation passes as a wave in a vacuum. While passing, it has two oscillations, which is due to electric and magnetic properties of that waves. And both the waves are sine waves. Sine waves means they are perpendicular to each other. Perpendicular waves. How it is interacted with the matter? When electric property of an electromagnetic radiation matches with the electric property of a matter, then the radiation interacts with the particular matter or an analyte. If a magnetic property of an electromagnetic radiation matches with the magnetic property of the matter, then it interacts with the particular characteristic of analyte. Thereby, the particular analyte is analyzed or characterized due to electromagnetic radiation, which is the application of electromagnetic radiation. So what is an electromagnetic radiation? The radiation which has both electric and magnetic properties. You can observe the picture for how it has electric and magnetic field oscillations and how it interacts with matter. Why particularly electromagnetic radiation is used to characterize a molecule? Since a molecule also has electric and magnetic properties, and the radiation also has electric and magnetic properties to analyze the particular molecule. That's why the radiation is used in spectroscopic analysis. Whenever electromagnetic radiation is used for analysis, then the technique is called spectroscopic analysis. So what are the key points we have got from the last two slides? What is spectroscopy? What is a matter? And what is an EMR? Next we'll move on to what are theories or properties of an electromagnetic wave. An electromagnetic wave has two properties or theories. One is wave theory, another one is particle theory or corpuscular theory. What is wave theory? It states about characterization of a wave in a vacuum. Characterization of a wave in a vacuum. You can observe the picture how wave theory works for a electromagnetic radiation. And the picture represents electromagnetic spectrum with different electromagnetic radiations with increasing wavelength and decreasing energy. Then observe the picture for how wave theory works on electromagnetic spectrum of radiations. It starts from gamma rays, X-rays, ultraviolet rays, infrared, visible, microwaves and radio waves. With the wavelength and frequency scale is mentioned in the picture, just observe that. What is particle or corpuscular or quantum theory? It states about energy of wave in the form of quanta or photons. Energy of wave in the form of quanta or photons. The formula represents the photons are energy equals to h nu. H is Planck's constant with the value of 6.626 into 10 to the power minus 34 joules second, and frequency nu is representing frequency. The picture represents the light as a wave phenomenon and light as stream of photons. So light exists as wave property and also exists as particle, so that it has two properties or two theories. A light here represents electromagnetic radiation, has two properties. One is wave property, another one is particle property. When light exists as wave, how it appears. When light exists as particle, how it appears. Particle means it is a photon. Wave means it passes like a wave. So combining both are applicable for analyzing a molecule when the radiation is passed on to the molecule. What are the properties of a wave according to wave theory? What are the properties of a wave according to wave theory? Wave length, wave number, frequency, velocity. These are wave properties as per wave theory. First, what is a wave? A wave has a peak and a trough. A peak and a trough. And the picture depicts a complete wave which has a peak and a trough or crest. And this wave is used to quantify a particular wave when it is used for analysis. What is wavelength? Wavelength is denoted with lambda. The distance between successive peaks and troughs are called as wavelength. The unit of measurement is nanometers, centimeters or angstrom. So distance unit is used to measure wavelength of a wave. It is between successive peaks or troughs are called as wavelength distance. And this wavelength is used in UV visible and X-rays analysis. What is wave number? It is denoted with nu bar. The number of waves per centimeter is known as wave number. The unit of measurement is centimeter inverse. How many waves are passed in a centimeter is called wave number. You can observe the picture. Within 2 centimeters, there are 4 cycles are passed. If with the same distance, if 8 cycles are passed, number of waves will be increased. So that how many number of waves, whole waves are passed in a centimeter is called wave number. And infrared radiation is measured by using wave number as a wave characteristic of IR. What is frequency? That is nu, mentioned with nu. The number of waves passed in a vacuum through a single point per second. The number of waves passed in a vacuum through a single point per second. The unit is hertz. Hertz or megahertz. or cycles per second, megacycles per second. Frequency unit is hertz or cycles per second. And frequency is measured based on time. Per second, how many waves are passed, where wave number is based on distance. In 1 centimeter, how many waves are passed? More or less similar. Both are directly proportional to each other, wave number and frequency. But wave number is measured based on distance, whereas frequency is measured based on time. Where higher radio waves and microwaves are measured with unit frequency. What is velocity? It is represented with c. It is the speed of light in the given distance per second. So velocity includes both distance and time. So it may comprises of wave number and frequency. The unit is centimeter per second or meter per second. And this velocity is used to measure energy of wave. When energy is high, velocity also high. And the wave speed is analyzed based on frequency and wavelength. So velocity is the product of frequency and wavelength. It is mentioned in the diagram. You can observe V equals to F into lambda. F represents frequency and lambda represents wavelength. Unit of that also has given, so that wave speed is getting unit as meter per second or centimeter per second. So in view of studying about energy of electromagnetic radiation, let's see the relationship between wavelength, wave number and frequency. When wavelength is increased, frequency is decreased. When wavelength is reduced, frequency is increased. Just recollect the points. What is wavelength, what is frequency, and what is wave number. When wavelength is increased, wave number also reduced and frequency also reduced. So wavelength is indirectly proportional to frequency and wave number. That is the relationship between wavelength, wave number and frequency. Let's see the relationship between wavelength, frequency and energy. So energy is directly proportional to frequency, as stated under particle theory of wave, that is E equal to h nu. E represents energy that is directly proportional to frequency of radiation. So automatically wavelength is indirectly proportional to energy. When wavelength is increased, energy is decreased. When wavelength is decreased, energy is increased. See the diagram. Short wavelength represents high frequency and high energy, where long wavelength represents low frequency and low energy. That is the relationship between wavelength, frequency and energy. Let's see what are the types of spectroscopy. There are two broad categories of spectroscopy. They are electronic and structural elucidation spectroscopy, where electronic spectroscopy is of absorption and emission. Absorption is of molecular and atomic, emission is of molecular and atomic. Example for molecular absorption is UV visible. Atomic absorption is atomic absorption spectroscopy. Whereas molecular emission is fluorimetry, atomic emission is atomic emission or flame emission spectroscopy. Coming to structural elucidation spectroscopy, examples are IR, NMR, ESR, MAS, XRD, that is X-ray, diffraction and polarimetry. Next column represents electromagnetic radiation used in each technique. In electronic spectroscopy, commonly used electromagnetic radiation is UV visible. For IR, infrared, NMR, radio waves, ESR, microwaves. In mass spectrometry, we are not using any electromagnetic radiation. And X-rays, polarimetry, UV visible radiation. And next column represents wave property and unit of measurement of each wave. UV visible wave is measured with wavelength and the unit is nanometer, whereas infrared wave number and the unit is centimeter inverse. Radio waves and microwaves with the frequency in megahertz, where mass spectroscopy no EMR, as so no unit is measured. And X-rays, wavelength with Armstrong unit, UV visible. For polarimetry, lambda in nanometers. And the next column represents particle property and interaction with matter. UV visible spectroscopy. In UV visible spectroscopy, molecules interacting with photon, where photon is interacting with atom. In fluorimetry, photon plus molecule, AES and FES, photon plus atom. IR, photon plus molecular vibration. And in NMR, photon plus nucleus. In ESR, photon plus unpaired electron. Mass, molecular mass is analyzed. And in XRD, photons plus crystals. In polarimetry, photons and chiral centers of a molecules are interacted. So if you understand the tabular column, it is very easy to study all the spectroscopy. It is a simplified form of spectroscopic analysis given here. And here are the types of spectroscopy with an overview of electronic spectroscopy. For absorption and emission, you can see the spectrophotometers appearance here. How it appears in the laboratory, you can find these instruments. For absorption, UV visible and atomic absorption. For emission, fluorimetry and flame emission, spectrophotometer. And observe the spectrophotometers for structural elucidation spectroscopy. First one is infrared, then NMR, then ESR, then mass spectrometry, then X-ray diffraction spectrometer, then polarimeter. So these are the instruments for various spectroscopic analysis are used in the industry or in the pharmaceutical laboratories. Thank you dear students for patient listening. Hope you all are able to follow my class. If you have any doubt, immediately ask after completely seeing this presentation. You just ask questions from the given notes and you should be able to answer for the question what you have raised on your own. If you are not able to answer, then post the question what you have got into your mind about spectroscopy and send to me in the Google Classroom app. I'll be explaining you. Thank you all. Stay home, stay healthy, stay safe.